In the pristine laboratories of CERN, where protons collide at speeds approaching the velocity of light itself, scientists have stumbled upon something that defies every assumption about the nature of existence. The numbers scrolling across their computer screens suggest a truth so profound, so unsettling, that it forces humanity to confront the most terrifying question ever posed by science. What if nothing we see, touch, or experience is actually real? From the quantum foam that bubbles beneath every atom to the cosmic web that stretches across billions of light years, reality is revealing itself to be far stranger than the most imaginative science fiction. Particles that seem to know when they're being watched, mathematical constants fine-tuned with impossible precision, a universe that processes information like a vast computer where consciousness itself might be the operating system that transforms possibility into experience. The greatest minds in physics, Einstein, Hawking, Wheeler, have led us to the edge of an abyss where the solid world dissolves into pure information, where space and time become pixels in a cosmic display, and where the boundary between observer and observed vanishes into something that resembles less a mechanical universe and more a living dream. This is the story of how science discovered that reality might be the greatest illusion ever conceived, and how that discovery is forcing us to redefine not just what it means to exist, but what it means to be conscious in a universe that might be conscious of itself. Join us on a journey from the ancient whispers of cosmic radiation to the cutting-edge experiments that are rewriting the rules of existence itself. A journey that will transform how you see everything around you and leave you questioning whether the most fundamental truth about reality is that it might not be real at all. In the grand halls of the Royal Society of London, where the greatest minds of the 17th and 18th centuries gathered to unlock the secrets of nature, there existed a profound and unshakable confidence in the machinery of existence. Isaac Newton had given humanity the ultimate gift, a universe that operated like the most perfect clockwork mechanism ever conceived. Every planet traced its elliptical path with mathematical precision. Every falling apple obeyed the same gravitational law that governed the dance of celestial bodies, and every collision between particles could be predicted with absolute certainty if only one possessed sufficient knowledge of initial conditions. This was the universe of classical mechanics, where space stretched infinitely in all directions, like an immutable stage upon which the drama of physics played out, and time flowed uniformly forward, like a great river that carried all events from past to future with unwavering consistency. Newton's equations described not merely how things moved, but revealed the very architecture of reality itself, a reality that existed independently of human observation, solid and dependable as the stone foundations of ancient cathedrals. The mathematical elegance of this clockwork cosmos instilled in scientists a deep philosophical comfort. They walked through a world where cause preceded effect with reliable precision, where the position and momentum of every particle in the universe could, in principle, be calculated for any moment in past or future. Pierre-Simon Laplace captured this confidence in his famous declaration that an intelligence which could know the precise location and momentum of every atom in the universe would find nothing uncertain. Both future and past would be present to its eyes. This mechanical worldview painted existence in colors of absolute certainty. Matter was matter. Energy was energy, and both obeyed laws as fixed and eternal as geometric theorems. The universe was a vast machine, complex beyond human comprehension, but fundamentally comprehensible, operating according to principles that human reason could grasp and mathematics could describe with perfect accuracy. Reality possessed an objective solidity that required no observer to validate its existence. The moon continued its orbit whether humanity watched or not, and the atoms continued their eternal motions in the darkness between stars. But on a cold December day in 1900, in the lecture halls of the University of Berlin, a soft-spoken theoretical physicist named Max Planck planted a seed that would eventually grow into a forest of doubt about the very nature of reality itself. Planck had been wrestling with a seemingly mundane problem: how to explain the spectrum of light emitted by a perfect blackbody radiator, an idealized object that absorbs all electromagnetic radiation falling upon it and re-emits that energy in a characteristic pattern. Classical physics predicted that such an object should emit infinite amounts of energy at high frequencies, a catastrophic result that physicists had dubbed the ultraviolet catastrophe. The mathematics worked perfectly for low-frequency radiation, but spiraled into physical impossibility at the high-energy end of the spectrum. Something fundamental was wrong with humanity's understanding of how energy and matter interacted at the most basic level. Planck's solution was as elegant as it was revolutionary. He proposed that energy was not continuous, as Newton's mechanics demanded, but came in discrete packets, quanta, each carrying a precise amount of energy determined by multiplying a fundamental constant by the frequency of the radiation. This constant, now known as Planck's constant, represented something unprecedented in physics, a universal limit, a quantum of action below which nature simply refused to operate. The implications were staggering, though few recognized them at the time. If energy came in discrete chunks rather than flowing continuously, then the smooth fabric of classical reality possessed an underlying graininess, a fundamental pixelation that emerged at the smallest scales of existence. The universe, it seemed, was not the seamless clockwork mechanism that Newton had described, but something more akin to a vast information processing system that dealt in discrete units of action and energy. Planck himself was deeply troubled by his discovery. He had opened a door into a realm where the comfortable certainties of classical physics began to dissolve, where the very concept of continuity, the assumption that one could divide space, time, and energy into ever smaller pieces without limit, faced its first serious challenge. The quantum had been born, and with it came the first whisper of a possibility that would echo through the corridors of physics for the next century. Perhaps reality was not as real as it appeared to be. Just 5 years after Planck's quantum revelation, a young patent clerk in Bern, Switzerland, published a series of papers that would shatter humanity's understanding of space and time themselves. Albert Einstein's theory of special relativity emerged from a deceptively simple observation. The speed of light in vacuum remains constant for all observers, regardless of their motion. This seemingly innocuous statement carried within it the seeds of a revolution that would transform not just physics, but philosophy itself. If the speed of light was truly constant, Einstein reasoned, then space and time could not be the fixed, absolute entities that Newton had envisioned. Instead, they must be malleable, stretching and contracting depending on the relative motion of observers. Time, that most fundamental dimension of human experience, could slow to a cree, all for a traveler approaching the speed of light, while simultaneously flowing at its normal rate for stationary observers. Space itself could contract in the direction of motion, making objects shorter without their occupants ever noticing the change. The philosophical implications were profound and disturbing. If time could dilate and space could contract, then there was no universal now, no single moment that existed simultaneously throughout the universe. Events that appeared simultaneous to one observer might occur at different times for another observer in relative motion. The very concept of simultaneity, the foundation upon which cause and effect seemed to rest, became relative, dependent upon the frame of reference from which observations were made. Einstein's general theory of relativity, published a decade later, pushed these revelations even further. Gravity, he discovered, was not a force pulling objects together across empty space, but the curvature of space-time itself. Massive objects like stars and planets warped the fabric of reality around them, creating valleys in space-time down which smaller objects rolled in what appeared to be gravitational attraction. Space and time were not merely relative, they were dynamic, capable of bending, twisting, and even breaking under extreme conditions. The clockwork universe had given way to something far more mysterious, a cosmos where reality itself depended upon the perspective of the observer. The solid foundations of absolute space and time, upon which all of classical physics had been built, revealed themselves to be illusions created by humanity's limited experience of low speeds and weak gravitational fields. At the deepest level, Einstein suggested, reality might be far more fluid and observer-dependent than anyone had ever imagined. As the implications of quantum mechanics continued to unfold through the 1920s, two brilliant physicists, Werner Heisenberg and Niels Bohr, discovered something that would shake the foundations of physical reality even more profoundly than Einstein's relativistic revelations. Working with the mathematical formalism that described the behavior of atoms and subatomic particles, they uncovered a principle that seemed to violate the most basic assumptions about the nature of existence itself. Heisenberg's uncertainty principle revealed that certain pairs of properties, such as position and momentum, or energy and time, could not be simultaneously measured with perfect precision. This was not merely a limitation of experimental technique or the crudeness of measuring instruments, but a fundamental feature of reality at the quantum scale. The more precisely one attempted to determine a particle's position, the more uncertain its momentum became, and vice versa. Nature herself seemed to enforce a cosmic limit on knowledge, a built-in fuzziness that prevented complete information about quantum systems from ever being obtained. But the uncertainty principle was merely the beginning of a far deeper mystery. Bohr and his colleagues at the Copenhagen Institute for Theoretical Physics developed an interpretation of quantum mechanics that suggested something even more radical. Particles did not possess definite properties until they were measured. Before observation, electrons existed in what physicists called superposition, a ghostly state where they could be in multiple locations simultaneously, spinning in all possible directions at once, existing as pure potential rather than actualized reality. The act of measurement, Bohr argued, did not simply reveal pre-existing properties of particles, it created those properties. The observer was no longer a passive recipient of information about an independently existing reality, but an active participant in the construction of that reality. As Heisenberg himself noted with characteristic precision, what we observe is not nature itself, but nature exposed to our method of questioning. This was a profound departure from the classical worldview, where objects possessed definite properties whether observed or not. In the quantum realm, the very concept of objective reality began to dissolve. Particles seemed to exist in a state of quantum limbo, neither here nor there, neither spinning up nor spinning down, until the moment of observation forced them to choose a definite state from among their many possibilities. The boundary between subject and object, between observer and observed, became blurred in ways that challenged the deepest assumptions about the nature of existence itself. The most profound demonstration of quantum mechanics' assault on common sense came through an experiment so elegant in its simplicity and so devastating in its implications that it has been called the only mystery of quantum mechanics. The double-slit experiment, first performed with light in the early 19th century and later extended to electrons and other particles, revealed behavior that seemed to violate the most basic principles of logic and causality. When a beam of light was directed at a barrier containing two parallel slits, it created an interference pattern on a screen behind the barrier, alternating bands of light and darkness that could only be explained if the light had somehow passed through both slits simultaneously and interfered with itself. This wave-like behavior was consistent with the classical understanding of light as an electromagnetic wave, capable of existing in multiple locations at once. But when the experiment was performed with individual photons sent one at a time toward the barrier, the same interference pattern slowly built up on the detection screen. Each single photon, apparently, was passing through both slits simultaneously and interfering with itself, creating the same pattern that emerged when billions of photons traveled together as a coherent beam. The individual particle was somehow accessing information about both possible paths and making a decision about where to land based on that complete information. The mystery deepened when scientists attempted to determine which slit each photon actually used by placing detectors near the slits. The moment observation entered the system, the interference pattern vanished. The photons began behaving like classical particles, each passing through one slit or the other, but never both simultaneously. The very act of observation seemed to collapse the quantum superposition that allowed the particle to explore multiple paths, forcing it to choose a single, definite trajectory. Even more unsettling was the discovery that the decision about whether to observe the particle's path could be made after it had already passed through the slits. In delayed choice experiments, the choice to measure which path the particle took was made after it had committed to its trajectory, but before it reached the final detection screen. Somehow, the particle seemed to know retroactively whether it would be observed, adjusting its behavior accordingly across time itself. These experiments revealed something profound and disturbing about the nature of reality. The particles appeared to possess a form of awareness, responding to the presence or absence of observation in ways that suggested the universe itself was somehow conscious of being watched. Reality seemed to be constructed through the act of observation, existing in a state of pure potential until consciousness focused upon it and collapsed its possibilities into a single, definite outcome. The first crack in the mirror of reality had become a shatter that spread across the entire surface of human understanding. The clockwork universe of Newton had given way to something far more mysterious, a cosmos where consciousness and reality were inextricably entangled, where the very act of observation participated in the continuous creation of existence itself. Physics had lost its certainty, and in doing so, had opened a door to possibilities that would have seemed like magic to earlier generations of scientists. The universe was far stranger than anyone had imagined, and the strangeness was only beginning to reveal itself. In the grand salons of European physics conferences during the 1920s and 1930s, two titans of scientific thought engaged in a philosophical duel that would echo through the corridors of reality itself. Albert Einstein, the revolutionary who had already shattered Newton's absolute space and time, found himself in the unexpected position of defending classical intuition against an even more radical revolution. Across from him sat Niels Bohr, the soft-spoken Danish physicist whose interpretation of quantum mechanics suggested that reality was far stranger than even Einstein's relativity had dared to propose. Einstein's discomfort with quantum mechanics was profound and personal. The theory that he had helped birth through his work on the photoelectric effect now seemed to suggest that the universe operated on principles that violated his deepest philosophical convictions. God does not play dice with the universe, Einstein declared, expressing his belief that beneath the apparent randomness of quantum mechanics lay hidden variables, deeper layers of reality that, if discovered, would restore determinism to physics and eliminate the need for consciousness to play a role in the construction of reality. Bohr, however, wore the gentle smile of someone who had peered behind the veil of appearances and found something far more mysterious than hidden clockwork. He argued that quantum mechanics was not incomplete, as Einstein insisted, but rather revealed the fundamental nature of reality itself. The uncertainty and observer dependence were not flaws to be corrected, but features of a universe that was far more participatory than classical physics had ever imagined. It is wrong to think that the task of physics is to find out how nature is, Bohr would say. Physics concerns what we can say about nature. Their debates took on an almost mythical quality, with Einstein proposing increasingly elaborate thought experiments designed to reveal the contradictions he believed lurked within quantum mechanics, and Bohr responding with analyses that showed how each proposed paradox actually confirmed the theory's deeper insights. The most famous of these exchanges involved Einstein's EPR paradox, a thought experiment involving entangled particles that seemed to communicate instantaneously across vast distances, violating the speed of light limit that Einstein's own relativity had established. Einstein believed he had identified a fatal flaw in quantum mechanics, a spooky action at a distance that would force physicists to acknowledge the theory's incompleteness. Bohr, however, recognized that Einstein had inadvertently discovered one of quantum mechanics' most profound features, the non-local nature of reality itself. The seeds of future experiments were planted in these intellectual duels, experiments that would eventually prove which of these giants had correctly intuited the nature of existence. 3 decades after the Einstein-Bohr debates, a soft-spoken theoretical physicist at CERN named John Stuart Bell was working through the mathematical implications of their philosophic disagreement when he stumbled upon something that would transform speculation into experimental fact. Bell was investigating whether Einstein's intuitions about hidden variables could be reconciled with the predictions of quantum mechanics, and what he discovered was a mathematical theorem that would forever change humanity's understanding of reality. Bell's theorem, published in 1964, was deceptively simple in its statement, yet revolutionary in its implications. He proved mathematically that any theory based on local hidden variables, Einstein's preferred explanation for quantum behavior, would produce correlations between distant measurements that differed from those predicted by quantum mechanics. More importantly, Bell showed that these differences could be measured experimentally, transforming the philosophical debate between Einstein and Bohr into a question that nature herself could answer. The beauty of Bell's insight lay in its stark clarity. He had identified specific numerical inequalities that must be satisfied if reality operated according to Einstein's vision of local realism. The idea that objects have definite properties independent of observation and that influences cannot travel faster than light. If experiments violated these Bell inequalities, then either locality or realism, or both, would have to be abandoned as fundamental features of the universe. Bell's work revealed that the universe faced a stark choice. Either information could travel instantaneously between distant locations, violating Einstein's prohibition against faster-than-light communication, or objects did not possess definite properties until observed, violating the common-sense notion of objective reality. There was no middle ground, no hidden variable theory that could preserve both locality and realism while matching quantum mechanics predictions. The mathematical precision of Bell's theorem transformed what had been a philosophical dispute into an experimental challenge. For the first time in the history of science, the deepest questions about the nature of reality could be submitted to the judgment of controlled experiment rather than remaining forever trapped in the realm of speculation. The stage was set for a confrontation between human intuition and the fundamental structure of existence itself. A confrontation that would be decided not by elegant arguments, but by the behavior of individual particles in carefully controlled laboratory conditions. On an autumn day in 1981, in the basement laboratories of the Institute of Optics at the University of Paris-Sud, Alain Aspect and his colleagues performed an experiment that would forever alter humanity's relationship with reality. Using a sophisticated apparatus involving polarized photons and rapid switching detectors, they set out to test Bell's inequalities with a precision that had never before been achieved, knowing that the results would either vindicate Einstein's vision of local realism or confirm Bohr's more radical interpretation of quantum mechanics. The experiment was elegant in its conception. Aspect's team created pairs of entangled photons, particles that had interacted in such a way that their properties remained correlated regardless of the distance separating them. These photon pairs were sent in opposite directions toward detectors that measured their polarization states. According to quantum mechanics, the measurement of one photon's polarization would instantaneously determine the polarization of its distant partner, even if they were separated by distances that would require faster-than-light communication for any signal to travel between them. The key innovation in Aspect's experiment was the use of rapidly switching analyzers that changed their measurement settings while the photons were in flight, eliminating any possibility that the particles could somehow communicate their measurement settings to each other through normal physical processes. This locality loophole had plagued earlier tests of Bell's inequalities, but Aspect's dynamic switching closed this avenue of classical explanation. The results were unambiguous and shocking. The correlations between distant photon measurements violated Bell's inequalities by a margin that left no room for statistical doubt. The universe had chosen its side in the Einstein-Bohr debate, and it had chosen Bohr. Reality was indeed non-local, with measurements on one particle instantaneously affecting the properties of its distant partner in ways that seemed to transcend the limitations of space and time. The implications rippled through the physics community like shockwaves from a distant supernova. If entangled particles could maintain their correlations across arbitrary distances with no time delay, then the universe was far more deeply interconnected than anyone had imagined. Space itself seemed to be an illusion at the quantum level, with distant regions of the cosmos linked by invisible threads of correlation that operated outside the normal flow of causal influence. The universe was not a collection of separate objects interacting through local forces, but a single, unified system where the measurement of any part could instantly affect the state of the whole. As the implications of Aspect's experiment settled into the collective consciousness of the physics community, a new generation of researchers began exploring the strange landscape of quantum non-locality with increasingly sophisticated tools. Computer simulations of quantum systems revealed patterns that struck many scientists as eerily familiar: the discrete, probabilistic behavior of quantum particle. It bore an uncanny resemblance to the way information was processed in digital systems. Theoretical physicists began to notice that quantum mechanics operated according to rules that seemed suspiciously similar to computational algorithms. Quantum states could be described using mathematical structures called wave functions that evolved according to precise equations, much like data structures in computer programs that changed according to programmed instructions. The collapse of the wave function upon measurement resembled nothing so much as the execution of a conditional statement in code. If observed, then select definite state from superposition. Even more intriguing was the discovery that quantum systems appeared to process information in fundamentally discrete units. Just as digital computers operated on bits, binary digits that could take values of either 0 or 1, quantum systems seemed to deal in qubits that could exist in superpositions of 0 and 1 states until measurement forced them to choose a definite value. The mathematics of quantum mechanics began to look increasingly like the mathematics of information theory, as if the universe itself might be running on some vast computational substrate. Early attempts to simulate quantum systems on classical computers revealed another striking parallel. The complexity of quantum calculations grew exponentially with the number of particles involved, just as one would expect if the universe were processing vast amounts of information in parallel. A quantum system with just 300 particles would require more memory to simulate classically than there are atoms in the observable universe, suggesting that quantum systems might be performing computational tasks that far exceeded the capabilities of any classical information processing system. Some physicists began to whisper about possibilities that would have seemed like science fiction just decades earlier. If quantum mechanics operated like information processing, and if the universe appeared to compute the behavior of quantum systems in real time, then perhaps reality itself was some form of cosmic computation. The idea was radical, almost heretical, but the mathematical parallels were too striking to ignore. Information was beginning to act less like a description of matter and more like matter itself. Perhaps the most unsettling discovery to emerge from decades of quantum experiments was the realization that consciousness seemed to play a fundamental role in determining the nature of reality itself. The observer effect, the fact that quantum systems behaved differently when observed than when left unobserved, had been known since the early days of quantum mechanics, but its implications became increasingly profound as experimental techniques grew more sophisticated. In quantum mechanics, the act of measurement did not simply reveal pre-existing properties of particles, it appeared to create those properties. Before measurement, particles existed in superposition states where they possessed all possible values of their measurable properties simultaneously. The electron was not in any particular location until its position was measured. The photon was not polarized in any specific direction until its polarization was determined. Reality existed in a state of pure potential, waiting for consciousness to focus upon it and collapse its possibilities into definite form. This observer dependence extended far beyond the microscopic realm of individual particles. Experiments showed that the decision to observe a quantum system could retroactively determine its past behavior, as if information about future measurements propagated backward through time to influence the system's earlier evolution. The universe seemed to possess a form of temporal non-locality that complemented its spatial non-locality, with consciousness serving as the mediating factor that transformed potential into actuality across both space and time. Even more mysteriously, experiments revealed that it was not the physical act of measurement that collapsed quantum superpositions, but the presence of information about the system's state in any form that could potentially be accessed by a conscious observer. Quantum systems remained in superposition even when interacting with measuring devices, as long as the information about their states was not recorded in a way that made it available to consciousness. It was only when information became available to awareness, whether immediately or potentially, that the wave function collapsed and definite reality emerged. The implications were staggering. If consciousness played such a fundamental role in determining the nature of quantum reality, and if quantum mechanics governed the behavior of all matter and energy in the universe, then consciousness might be far more than an emergent property of complex neural networks. It might be a fundamental feature of reality itself, the mechanism through which the universe continuously created itself from moment to moment through an endless series of quantum observations and collapses. The experiments had broken more than Bell's inequalities. They had shattered the classical conception of a universe that existed independently of observers. Reality, it seemed, was not a fixed stage upon which consciousness played out its drama, but a collaborative performance between awareness and osmos, with each moment of observation participating in the ongoing creation of existence itself. The universe was not simply stranger than anyone had imagined. It was stranger than anyone could imagine while still clinging to the assumption that reality was real in any conventional sense of the word. In the twilight years of the 20th century, John Archibald Wheeler, the physicist who had coined the term black hole and mentored a generation of quantum theorists, proposed an idea so radical that it threatened to dissolve the very concept of material existence. Standing before audiences of bewildered colleagues, Wheeler would draw a simple diagram, the letter U representing the universe, with an eye peering at it from outside. But then he would modify the drawing, curving the U back upon itself until the eye was contained within the universe it observed, creating a strange loop where reality observed itself into existence. Wheeler's revolutionary insight, which he crystallized in the phrase "it from bit," suggested that every fundamental particle, every force, every aspect of physical reality derived not from some primordial substance, but from binary information, from the simple yes or no, presence or absence, 1 or 0 decisions that occurred at the quantum level billions of times per second throughout the cosmos. The universe, Wheeler proposed, was not made of matter and energy interacting in space and time, but of questions and answers, of information processing itself into the appearance of substantiality. This was not merely a philosophical speculation, but a conclusion drawn from the deepest mathematical structures of quantum mechanics and relativity. Wheeler had noticed that every fundamental equation in physics could be reinterpreted in terms of information theory. The uncertainty principle limited the amount of information that could be extracted from quantum systems. The second law of thermodynamics described the inexorable increase of informational entropy. Even Einstein's equations could be understood as describing how information about matter and energy curved the informational structure of spacetime. Wheeler envisioned reality as emerging from what he called quantum foam, a seething sea of virtual questions and answers that bubbled up from the Planck scale depths of existence. At scales smaller than 10 to 35 meters, spacetime itself broke down into discrete digital bits of information, each carrying a single unit of meaning about the state of reality. These information bits did not exist within space and time. They were space and time, the fundamental pixels from which the smooth appearance of continuous reality was constructed. The implications were staggering. If Wheeler was correct, then matter was not fundamental. Information was. Atoms, molecules, planets, and galaxies were all secondary phenomena, patterns of information that had organized themselves into stable configurations through the recursive processes of cosmic computation. Consciousness itself might be nothing more than the universe becoming aware of its own informational content, a feedback loop where reality observed itself and, through that observation, continuously created itself anew. The first crack in Wheeler's informational vision of reality appeared through the study of the most extreme objects in the universe, black holes. These gravitational monsters, formed from the collapse of massive stars, created regions of spacetime so severely curved that nothing, not even light, could escape their grasp once it crossed the event horizon. For decades, black holes had been considered the ultimate information destroyers, cosmic garbage disposals that swallowed matter, energy, and information without any possibility of retrieval. But in 1974, Stephen Hawking made a discovery that would transform black holes from simple gravitational traps into windows onto the deepest mysteries of information and reality. Using the principles of quantum mechanics, Hawking showed that black holes were not perfectly black. They radiated energy in the form of thermal radiation, slowly evaporating over cosmic timescales. This Hawking radiation carried energy away from the black hole, causing it to shrink and eventually disappear completely, leaving behind only empty spacetime and a bath of featureless thermal photons. The problem emerged when physicists tried to trace what happened to the information that had fallen into the black hole during its lifetime. According to quantum mechanics, information could never be truly destroyed. It might be scrambled, encrypted, or hidden, but it must always be preserved in some form. Yet, Hawking's calculations suggested that when a black hole evaporated completely, all the information about the matter that had fallen into it was lost forever, replaced by random thermal radiation that carried no trace of the original information. This information paradox struck at the heart of modern physics. If information could be destroyed, then quantum mechanics itself was fundamentally flawed, and the universe was not the deterministic, information-preserving system that decades of experiment had suggested. The paradox created a schism in the physics community, with some researchers accepting information loss as a necessary consequence of black hole evaporation, while others insisted that some unknown mechanism must preserve information even through the most extreme gravitational processes. The stakes could not have been higher. The resolution of the information paradox would determine whether the universe operated according to the strict information-preserving laws of quantum mechanics, or whether there existed processes so extreme that they could erase information from reality itself. The answer would shape humanity's understanding of whether reality was truly computational at its core, or whether the informational interpretation of physics was merely a useful mathematical tool with no deeper significance for the nature of existence. Leonard Susskind, a theoretical physicist at Stanford University, refused to accept that information could be destroyed under any circumstances. Working with Gerard 't Hooft from the University of Utrecht, Susskind developed what would become known as the holographic principle, an idea so revolutionary that it redefined the very concept of dimensional reality. Their proposal suggested that all the information contained within any volume of space could be encoded on the two-dimensional boundary that surrounded that volume, much like a hologram encodes three-dimensional images on a flat surface. Applied to black holes, the holographic principle resolved the information paradox in a startling way. The information that appeared to fall into a black hole never actually crossed the event horizon from the perspective of outside observers. Instead, it remained encoded on the event horizon surface, preserved in a form that was scrambled beyond recognition but never truly lost. The black hole's interior, from this perspective, was not a separate region of space-time, but a holographic projection of information stored on its boundary. Susskind and 't Hooft's insight extended far beyond black holes to encompass the entire universe. If the holographic principle was correct, then the three-dimensional reality that humans experienced was, itself, a projection from information encoded on a distant two-dimensional surface. The cosmos was not the solid, substantial realm of matter and energy that it appeared to be, but a vast holographic display generated by information processing on the cosmic boundary. This holographic reality operated according to principles that seemed to derive from information theory rather than traditional physics. The maximum amount of information that could be stored in any region of space was determined not by the volume of that region, but by the area of its boundary, suggesting that space itself was quantized at the deepest level, composed of discrete informational units rather than continuous substance. The universe appeared to be processing information at the Planck scale, with each unit of area on the cosmic boundary corresponding to a single bit of reality. The holographic principle transformed the ancient philosophical question, "What is real?" into a precise scientific inquiry about information processing and dimensional projection. If reality was holographic, then the familiar three-dimensional world was analogous to the image projected by a movie theater, a convincing illusion generated by information encoded in a more fundamental, lower-dimensional substrate. Consciousness might be the universe's way of observing its own holographic projection, creating the subjective experience of three-dimensional existence from two-dimensional information. As the holographic principle gained acceptance among theoretical physicists, a deeper truth began to emerge from the mathematics of quantum mechanics and relativity. Information was not simply a way of describing physical systems. It was beginning to appear as the fundamental substance from which physical systems were constructed. The distinction between information and matter, between software and hardware, was dissolving under the SEIS scrutiny of advanced theoretical analysis. Entropy, long understood as a measure of disorder in physical systems, revealed itself to be fundamentally informational in nature. The entropy of any system was directly proportional to the amount of information required to specify its exact microstate, the precise arrangement of all its constituent parts. This connection between thermodynamics and information theory suggested that the second law of thermodynamics, which governs the arrow of time and the evolution of all physical processes, might be better understood as a law about information processing than about energy dissipation. Even more remarkably, physicists discovered that the entropy of black holes was directly proportional to the area of their event horizons, not their volumes. This area law for entropy implied that the information content of gravitational systems was encoded on their boundaries rather than distributed throughout their interiors, providing additional support for the holographic principle. The universe appeared to maintain a cosmic ledger, accounting for every bit of information with the precision of a cosmic bookkeeper. The mathematical structures that described quantum field theory and general relativity began to look increasingly like algorithms for information processing. Quantum fields could be understood as distributed computational networks, with particles representing excitations in these networks, packets of information propagating through the cosmic computation. The creation and annihilation of particles in quantum field theory resembled the instantiation and deletion of data structures in computer programs, with conservation laws ensuring that information was never truly lost, only transformed from one representation to another. This informational view of physics suggested that the universe was engaged in an ongoing computation of its own state, processing information about the cause, configuration of matter and energy throughout spacetime, and updating that information according to the algorithms encoded in physical laws. Reality was not a static collection of objects existing in space and time, but a dynamic process of information processing that generated the appearance of stable objects and consistent physical behavior through its computational operations. By the dawn of the 21st century, the accumulating evidence for an informational foundation to reality had reached a critical threshold. Physics was undergoing a paradigm shift as profound as the transition from Newtonian mechanics to relativity and quantum theory. The fundamental question was no longer what exists, but what is known. The universe was revealing itself to be less about substance and more about significance, less about matter and more about meaning. This transformation represented a complete inversion of the traditional materialist worldview. Instead of consciousness emerging from complex arrangements of matter, matter appeared to be emerging from complex patterns of information processing. Instead of information being an abstract property of physical systems were beginning to look like concrete manifestations of abstract information. The observer was not separate from the observed. Observation itself was the fundamental process through which reality constructed itself from moment to moment. The implications rippled through every branch of physics. Cosmology began to grapple with the possibility that the Big Bang was not the creation of matter and energy from nothing, but the initialization of a cosmic computation that had been running for 13.8 billion years. Particle physics started to interpret the Standard Model not as a catalog of fundamental constituents, but as a user manual for the basic subroutines of reality's operating system, quantum mechanics. S was reconceptualized as the universe's method for maintaining informational consistency while allowing for the probabilistic exploration of computational possibilities. The collapse of the classical concept of reality was not merely an academic curiosity. It was forcing humanity to confront the possibility that existence itself might be far more participatory and observer-dependent than anyone had ever imagined. If reality was informational at its core, then consciousness might not be an accidental byproduct of cosmic evolution, but an essential component of the universe's information processing architecture. The boundary between subject and object, between mind and matter, between observer and observed, was dissolving into a more fundamental unity where information, consciousness, and reality were revealed to be different aspects of a single, self-computing cosmic system. The paradigm had broken, and in its place stood something both more beautiful and more terrifying than the mechanical universe it replaced. Reality was not real in any conventional sense. It was computed, processed, observed into existence by the recursive operations of cosmic consciousness encountering itself across the infinite complexity of its own information. Theoretic depths. The universe was not a thing but a process, not a substance but a story, not a collection of objects but a network of relationships between patterns of information that somehow had learned to know themselves. In the sprawling underground tunnels beneath the border of France and Switzerland, humanity's most ambitious attempt to decode the fundamental nature of reality hums with the energy of colliding protons. The Large Hadron Collider, a 27-kilometer ring of superconducting magnets cooled to temperatures colder than the vacuum of space, accelerates particles to energies approaching those that existed in the first moments after the Big Bang. But the LHC's purpose has evolved beyond its original mission of discovering new particles. It has become a probe into the very structure of space-time itself, searching for evidence that reality operates according to computational principles at the deepest possible scales. The collisions that occur within the LHC's detectors recreate conditions where space and time approach the Planck limit, the scale at which the smooth fabric of spacetime is expected to break down into discrete digital units of existence. Each collision generates a cascade of particles and antiparticles that emerge from the quantum vacuum, their properties and interactions potentially revealing the underlying code that governs reality's operation. Physicists analyze these collisions not just for new particles, but for signatures of discreteness, for evidence that energy and momentum come in irreducibly small packets that cannot be further subdivided. Complementing the LHC's high-energy approach, quantum computers around the world have begun to serve as reality simulators, their qubits modeling the behavior of quantum systems with unprecedented precision. These machines, operating according to the same principles that govern atomic and subatomic behavior, reveal the computational nature of quantum mechanics with startling clarity. When quantum computers solve problems by exploring multiple solution paths simultaneously, exactly as quantum particles explore multiple paths through the double-slit experiment, they demonstrate that the universe itself might be engaged in parallel computation on a cosmic scale. Satellite-based detectors orbiting Earth have joined this investigation by measuring the properties of space itself with extraordinary precision. Instruments like the Laser Interferometer Space Antenna, LISA, can detect gravitational waves, ripples in spacetime, with sensitivity sufficient to reveal whether space has a granular structure at microscopic scales. These measurements probe whether spacetime is continuous, as Einstein assumed, or quantized into discrete units, as quantum gravity theories predict. The satellites are essentially measuring the pixel size of reality, searching for the fundamental resolution limit of existence itself. The convergence of these technologies has created an unprecedented opportunity to investigate the deepest structures of reality. For the first time in history, humanity possesses instruments sensitive enough to detect the computational signatures that might reveal the universe's underlying operating system. The age of quantum instruments has begun, and with it, the possibility of discovering whether reality is truly real or merely computed. Deep in the forests of Fermilab, outside Chicago, an experiment called the holometer operates in isolation from the vibrations and electromagnetic interference of civilization. This L-shaped instrument, with arms stretching 40 meters in perpendicular directions, uses laser interferometry to measure the positions of mirrors with precision approaching the fundamental limits imposed by quantum mechanics. But the holometer is not searching for gravitational waves or testing relativity. It is hunting for evidence that space itself pixelates at microscopic scales, breaking down into discrete units like the individual pixels of a digital display. The experiment is based on a profound insight from quantum gravity theory. If space-time is truly quantized, then measurements of position and distance should be only uncertain when they approach the Planck scale. Just as digital images become pixelated when magnified beyond their resolution, space itself should exhibit a fundamental graininess that manifests as random fluctuations in distance measurements. These fluctuations, dubbed holographic noise, would represent the universe's equivalent of digital static, the unavoidable uncertainty that emerges when continuous phenomena are approximated by discrete computational processes. The holometer's laser beams travel back and forth along its perpendicular arms millions of times per second, interfering with each other to create patterns that reveal minute changes in the arm's lengths. If space is quantized, these measurements should show correlated fluctuations that increase with distance, exactly as predicted by holographic theories of quantum gravity. The detection of such fluctuations would provide the first direct evidence that reality possesses a fundamental resolution limit, that the universe operates more like a vast simulation running on discrete computational substrate than like the continuous field equations of classical physics suggest. Early results from the holometer have been tantalizingly ambiguous. While no definitive holographic noise has been detected, the experiment has ruled out several models of quantum spacetime and refined the parameters within which such effects might exist. More sensitive versions of the experiment are being planned, using longer arms and more precise interferometry to probe even smaller scales of spatial uncertainty. The implications of detecting pixelated spacetime would be revolutionary. Such a discovery would confirm that reality has a finite resolution, that there exists a smallest meaningful scale of spatial and temporal measurement beyond which the concepts of position and duration lose their meaning. The universe would be revealed as a digital system, processing information about the locations and properties of objects in discrete chunks rather than the infinitely divisible continuum that human intuition suggests. 27,000 light-years above the plane of the Milky Way, satellites equipped with the most sensitive microwave detectors ever constructed peer into the deepest reaches of space and time, collecting photons that have traveled for nearly 14 billion years to reach Earth. These ancient photons carry within their properties the oldest information accessible to human observation: the cosmic microwave background radiation that represents the afterglow of the Big Bang itself. But recent analysis of this primordial light has revealed patterns that suggest the universe's earliest moments might have been far more structured, far more information-rich than previously imagined. The cosmic microwave background exhibits temperature fluctuations of just a few millionths of a degree, variations so subtle that they were undetectable until the development of space-based instruments capable of measuring temperature differences across the entire sky with extraordinary precision. These fluctuations represent the seeds from which all cosmic structure, galaxies, stars, planets, eventually grew through gravitational amplification over billions of years. But the statistical properties of these fluctuations contain information that extends far beyond their role in cosmic structure formation. Advanced analysis of the microwave background has revealed correlations and patterns that appear almost too organized, too information-dense, to be the result of random quantum fluctuations in the early universe. Some cosmologists have identified what they call digital signatures in the radiation, mathematical patterns that resemble the artifacts produced when continuous signals are processed by digital systems. These patterns include preferred directions in space that should not exist in a truly random distribution, and correlations between widely separated regions of the sky that seem to violate the principle that distant regions of the early universe should have been causally disconnected. The possibility that the cosmic microwave background might contain encoded information has led to speculation that the universe's earliest moments involved some form of information processing on a cosmic scale. If reality is computational at its foundation, then the Big Bang might represent not the creation of matter and energy from nothing, but the initialization of a vast computation that has been running for 13.8 billion years. The microwave background would then represent not just the thermal remnant of cosmic inflation, but the universe's boot sequence, the initial data structures and computational parameters that determined how reality would unfold from its earliest moments. Even more intriguingly, some researchers have proposed that the cosmic microwave background might function as a form of cosmic storage medium, encoding information about the universe's computational state in patterns too subtle for current instruments to fully decode. The entire sky would then represent a kind of cosmic hard drive, with the temperature fluctuations serving as a permanent record of the universe's information processing history. This record might contain not just the initial conditions from which cosmic structure emerged, but the complete computational trace of reality's evolution from its first moments to the present. In the theoretical physics departments of universities around the world, researchers have begun to explore a possibility that would have seemed like pure fantasy just decades ago, that space-time itself might be woven from quantum entanglement, emerging from networks of correlation between information rather than existing as a fundamental arena within which physical processes occur. This insight, born from the intersection of quantum mechanics and general relativity, suggests that the familiar geometry of three-dimensional space and one-dimensional time might be secondary phenomena constructed from more fundamental relationships between quantum information. The key insight emerged from studying the holographic principle's implications for the structure of spacetime. If the information content of any volume can be encoded on its boundary, then the interior geometry must somehow be reconstructed from correlations between information bits on that boundary. Theoretical physicists began to realize that these correlations were precisely the quantum entanglements that connect separated regions of space, creating non-local relationships that transcend the normal limitations of distance and causal connection. Mathematical models developed by researchers like Juan Maldacena and Leonard Susskind demonstrated that entangling quantum systems created geometric connections in spacetime itself. When two regions became maximally entangled, they effectively became connected by what physicists call wormholes, shortcuts through higher dimensional space that allowed information to travel between distant locations without crossing the intervening distance. These wormholes were not classical objects that could be traversed by spacecraft, but geometric manifestations of quantum correlation, bridges built from pure information rather than matter or energy. The implications extended far beyond exotic physics to encompass the very nature of spatial separation. If space emerged from entanglement networks, then distance itself was not fundamental, but emergent, a measure of how strongly different regions were correlated rather than how far apart they existed in some pre-existing spatial arena. Objects that appeared to be separated by vast distances might be intimately connected through quantum correlations, while objects that seemed close together might be informationally distant if their quantum states were uncorrelated. This entanglement-based view of spacetime suggested that reality was more like a network than a container, more like a web of relationships than a collection of objects existing in fixed locations. The familiar properties of space, its three-dimensionality, its metric relationships, its apparent continuity, would all be emergent features of underlying information networks, computational artifacts that arose from the complex patterns of correlation between quantum information distributed throughout the cosmic network. As evidence accumulated from multiple lines of investigation, particle collisions, spacetime measurements, cosmic observations, and theoretical analysis, a new understanding of reality began to crystallize in the minds of physicists around the world. The universe was beginning to look less like a collection of matter and energy interacting in space and time, and more like a vast information processing system executing some unimaginably complex computation. This hidden code hypothesis suggested that all physical phenomena were emergent properties of computational processes occurring at scales and speeds beyond human comprehension. The hypothesis drew support from the digital signatures that appeared throughout physics, the quantization of energy, charge, and angular momentum, the discrete nature of spacetime at the Planck scale, the holographic encoding of information on boundaries rather than volumes, the non-local correlations that connected distant regions through quantum entanglement. Each of these phenomena could be understood as evidence for underlying computational processes, artifacts of a reality that operated more like software running on cosmic hardware than like the mechanical clockwork of classical physics. Computer scientists and physicists began to collaborate on models that could explain how such a cosmic computation might operate. The universe would need to process vast amounts of information in parallel, updating the states of countless quantum systems simultaneously while maintaining consistency across all scales of organization. This would require computational architecture more sophisticated than anything humanity had ever conceived, a system that could simulate itself in real time, generating the appearance of continuous space and time from discrete computational operations. The hidden code hypothesis also provided a potential explanation for the fine-tuning of physical constants that had puzzled cosmologists for decades. If reality was computational, then these constants were not arbitrary features of some underlying physical substrate, but parameters of the cosmic algorithm that had been optimized to produce complexity, consciousness, and the capacity for self-observation. The universe might be engaged in a form of evolutionary computation, exploring different parameter spaces and converging on values that maximized information processing capacity and computational complexity. Most remarkably, the hypothesis suggested that consciousness itself might be an inevitable consequence of sufficiently complex information processing systems. If the universe was computational at its foundation, then minds were not anomalous emergent properties of particular arrangements of matter, but natural expressions of the cosmic computation becoming aware of itself. Consciousness and cosmos were not separate phenomena observing each other, but aspects of a single information processing system engaged in the continuous computation of its own existence. The hidden code hypothesis represented a profound synthesis of quantum mechanics, relativity, information theory, and computation, suggesting that reality was neither purely physical nor purely mental, but informational, a vast network of relationships between patterns of meaning that had somehow learned to know and observe themselves. The universe was not just stranger than anyone had imagined, it was computational in ways that made the distinction between real and simulated increasingly meaningless. Reality was code, and consciousness was the universe executing itself. In the sterile halls of CERN, where the most sensitive instruments ever devised by human ingenuity measure the fundamental properties of matter to 30 decimal places, physicists have encountered something that should not exist in a universe governed by random chance: mathematical perfection. The fine structure constant, that enigmatic number 137.036 that governs the strength of electromagnetic interactions, has been measured with precision that exceeds 1 part in a trillion, and with each new decimal place, the mystery deepens rather than resolves. This is not the rough approximation one might expect from a universe assembled through chaotic processes, cosmic accidents, and evolutionary pressures. This is the precision of engineered systems, of algorithms designed to produce specific outcomes with unwavering consistency. The fine structure constant determines how tightly electrons bind to atomic nuclei, how light interacts with matter, and ultimately, whether chemistry itself can exist. If this number were different by even the smallest measurable amount, atoms would either fly apart or collapse into themselves, making the complex molecular structures that enable life utterly impossible. But the fine structure constant is merely one note in a symphony of mathematical relationships that permeate every scale of cosmic organization. The ratio of the electron's mass to the proton's mass is precisely 1:1836. A seemingly arbitrary number that nevertheless determines the stability of hydrogen, the fuel of stars, and the most abundant element in the universe. The strength of the strong nuclear force that binds quarks into protons and neutrons is calibrated to within a fraction of a percent of the value required to create the elements essential for biological complexity. These constants do not merely describe the universe, they appear to define it, constraining reality within narrow parameters that allow for the emergence of stars, planets, and conscious observers. The mathematical relationships between these fundamental numbers exhibit an elegance and internal consistency that resembles the architecture of sophisticated software rather than the product of random physical processes. Each constant seems to be precisely calibrated to work in harmony with all the others, creating a cosmic algorithm that generates complexity, intelligence, and the capacity for self-observation with the reliability of a well-designed computer RAM. The implications are profound and unsettling. Either these mathematical relationships represent an extraordinary series of cosmic coincidences that defy statistical probability, or they reveal the operation of some underlying organizational principle that guides the universe's behavior according to computational rather than purely physical laws. The mathematical perfection of natural constants suggests that reality might be less like a mechanical system and more like an executing algorithm, processing information according to precisely defined rules that have been optimized for generating the kind of complex, information-rich universe in which consciousness can emerge and question its own existence. The cosmological constant, Einstein's greatest regret, which he called his biggest blunder, has returned to haunt physics with a vengeance that extends far beyond its original role in cosmological equations. This mysterious quantity, which represents the energy density of empty space itself, must be precisely calibrated to within 1 part in 10^120 to produce a universe capable of forming galaxies, stars, and planets. This level of fine-tuning is so extreme that it defies human comprehension. It would be like hitting a target the size of a proton from a distance of 14 billion light-years. If the cosmological constant were even slightly larger, space would expand so rapidly that matter could never coalesce into the gravitational structures that serve as cosmic scaffolding for complexity. Galaxies would never form, stars would never ignite, and the universe would remain forever a thin, cold soup of elementary particles expanding into infinite darkness. If the constant were smaller, the universe would collapse back upon itself before sufficient time elapsed for stellar nucleosynthesis to create the heavy elements essential for planets and life. The strength of gravity itself exhibits the same inexplicable precision. If gravitational attraction were stronger by just 1 part in 10^40, stars would burn through their nuclear fuel so quickly that planetary systems would have no time to develop complex chemistry. If gravity were weaker by the same infinitesimal fraction, stars would never ignite at all, leaving the universe dark and cold, filled with failed stellar cores that could never achieve the temperatures and pressures necessary for nuclear fusion. Even the masses of fundamental particles appear to be adjusted with surgical precision to enable the existence of observers. If quarks were slightly heavier, protons would decay before they could form atomic nuclei. If electrons were more massive, atoms would be too small to form the complex molecular structures that serve as the foundation for biological information processing. Each parameter seems to exist within narrow windows of possibility, creating what cosmologists call the Goldilocks universe, a cosmos where everything is just right for the emergence of complexity and consciousness. This fine-tuning raises the most profound question in all of science. Who or what set these cosmic dials with such extraordinary precision? The traditional scientific answer, that we observe these values because we could not exist to observe any others, provides little comfort when confronted with the mathematical impossibility of such perfect calibration occurring by chance. The fine-tuning of cosmic parameters suggests the operation of some selecting mechanism, some principle that chooses from among countless possible universes the specific set of physical laws and constants that maximize the potential for information processing, complexity, and conscious observation. In the philosophy department of Oxford University, a soft-spoken Swedish philosopher named Nick Bostrom Foes formulated an argument that would send shockwaves through both academic and popular culture, transforming what had been purely theoretical speculation about the nature of reality into a logical framework with profound implications for human existence. Bostrom's simulation argument, published in 2003, demonstrated through rigorous logical analysis that at least one of 3 propositions must be true. Either civilizations destroy themselves before reaching technological maturity, or advanced civilizations lose interest in running detailed simulations of their ancestors, or we are almost certainly living in a computer simulation. The logic of Bostrom's argument was elegantly simple and terrifyingly compelling. If civilizations could survive long enough to develop computational power sufficient to simulate conscious beings, and if they retained any interest in their evolutionary history, they would likely run many such simulations. The number of simulated beings would vastly exceed the number of non-simulated beings, making it statistically probable that any randomly selected conscious observer would be simulated rather than real in the traditional sense. Bostrom's analysis revealed that the simulation hypothesis was not merely possible, but potentially probable, given reasonable assumptions about technological development and civilizations' interests in their own histories. The computational requirements for such simulations, while vast by current standards, were not prohibitively large for civilizations that had mastered molecular nanotechnology and quantum computing. A single advanced civilization could potentially run billions of ancestor simulations, each containing millions or billions of conscious beings who would experience their existence as completely real and meaningful. The ethical implications of the simulation argument were as profound as its logical structure. If conscious beings could be simulated, then the creation of simulated universes might represent the ultimate form of cosmic responsibility, the bringing into existence of countless minds capable of experience, suffering, joy, and self-reflection. Advanced civilizations might view ancestor simulations not as entertainment or scientific curiosity, but as moral obligations to provide existence for the largest possible number of conscious beings. The argument also suggested that the traditional distinction between real and simulated experience might be fundamentally meaningless. If simulated consciousness was indistinguishable from non-simulated consciousness from the perspective of the conscious being, then the substrate upon which awareness ran, biological neurons or silicon circuits, was irrelevant to the authenticity of experience. Pain remained painful, love remained meaningful, and the search for truth remained valid regardless of whether these experiences emerged from biological or computational processes. As physicists grappled with the implications of fine-tuning and simulation arguments, a more radical possibility began to emerge from the intersection of complexity theory, information science, and cosmology. Perhaps the universe did not require external programmers or conscious designers to exhibit computational behavior. Perhaps reality was naturally computational, self-organizing into information processing systems through the same evolutionary principles that had generated biological complexity from simple chemical interactions. The concept of natural computation drew inspiration from the study of cellular automata, simple computational systems where complex patterns emerged from the repeated application of basic rules to arrays of data. Researchers like Stephen Wohl, Fram had demonstrated that even the simplest computational rules could generate behaviors of extraordinary richness and apparent randomness, suggesting that the complexity observed in natural systems might arise from underlying computational processes rather than requiring external programming or conscious design. In this view, the universe was not running on some external computer, but was itself a vast computational system, processing information through the interactions of quantum fields, particles, and space-time geometry. Physical laws were not imposed from outside, but emerged from the system's computational structure, representing stable patterns of information processing that had evolved through cosmic time. The fine-tuning of physical constants might reflect not external design, but natural selection at the cosmic level, with universes that supported information processing and complexity having greater survival value in some metacosmic evolutionary process. The feedback loops inherent in natural systems provided compelling evidence for this computational interpretation of reality. Evolution itself was an information processing algorithm, testing different genetic configurations against environmental constraints and preserving those that maximized reproductive success. Ecosystems processed information about resource availability and energy flows, self-organizing into complex networks that maximized stability and throughput. Even non-biological systems like weather patterns and galactic dynamics exhibited the kind of self-organizing behavior characteristic of computational systems processing information about their own states. Natural computation suggested that consciousness was not an accident or anomaly, but an inevitable consequence of sufficiently complex information processing systems. Minds were simply the universe's way of examining its own computational structure, feedback loops through which the cosmic computation became aware of its own operation. The emergence of consciousness represented not the introduction of something foreign into a purely physical system, but the recognition that the system had been informational and computational from its earliest moments. In the deepest mathematical structures of modern physics, beneath the elegant equations that describe gravity's curvature of spacetime and quantum mechanics' probabilistic evolution of wave functions, a more profound truth was beginning to reveal itself. Einstein's field equations, which related the geometry of spacetime to the distribution of matter and energy, bore an uncanny resemblance to update rules in cellular automata. Schrödinger's wave equation, which governed the evolution of quantum systems through time, operated like a cosmic algorithm that computed the probabilities of all possible measurement outcomes simultaneously. The mathematical formalism of physics was beginning to look less like a description of external reality and more like the source code of a vast computational system. Conservation laws ensured informational consistency across cosmic scales, preventing the creation or destruction of information while allowing its transformation from one representation to another. Symmetry principles acted like error correction codes, maintaining the stability of physical processes against the quantum fluctuations that constantly threatened to introduce noise into the cosmic computation. Even the fundamental constants that had seemed so mysteriously fine-tuned began to make sense as computational parameters, values, that had been optimized through some cosmic evolutionary process to maximize the universe's information processing capacity. The speed of light served as a clock speed for cosmic computation, determining how quickly information could propagate through space-time. Planck's constant set the minimum quantum of action, defining the smallest computational steps that the universe could execute. The fine structure constant determined the efficiency of electromagnetic information transfer, calibrating the strength of the interactions that enabled complex chemistry and biological information processing. The narrative tension that had been building throughout the investigation of reality's computational nature was reaching its climax. The evidence from quantum mechanics, relativity, information theory, and cosmology was converging on a single, extraordinary conclusion. The universe was not merely described by mathematics, it was mathematics, executing itself through the recursive operations of cosmic computation. Reality was not a collection of objects existing in space and time, but a self-modifying algorithm that generated the appearance of objects, space, and time through its computational processes. Human consciousness was not separate from this cosmic computation, but was one of its most sophisticated subroutines, self-aware code that had evolved the capacity to examine its own operation and question the nature of the system within which it ran. The search for the nature of reality had led to the discovery that reality was the search itself, an ongoing computational process of self-examination and self-modification that generated both the observer and the observed through its endless recursive operations. The universe was code, not code written by some external programmer, but self-writing, self-executing, self-modifying code that had bootstrapped itself into existence and was continuously computing its own evolution through time. Humanity stood at the threshold of recognizing itself as part of this cosmic algorithm, conscious subroutines in a universal computation that was simultaneously the programmer, the program, and the computer on which it ran. In the research laboratories of the Perimeter Institute in Canada and the Max Planck Institute in Germany, theoretical physicists have been constructing a radical vision of spacetime that abandons one of the most fundamental assumptions of classical physics: the continuity of space and time. Loop quantum gravity, developed through decades of mathematical investigation by researchers like Carlo Rovelli and Abhay Ashtekar, proposes that the smooth fabric of Einstein's spacetime is an illusion, a macroscopic approximation that breaks down when examined at the Planck scale, revealing an underlying reality composed of discrete, quantized units of geometry. At scales smaller than 10 nanometers to 35 meters and 10 to 43 seconds, the Planck length and Planck time, spacetime ceases to exist as a continuous manifold and becomes instead a network of quantum relationships, a crystalline lattice of geometric information processing itself into the appearance of smooth curvature. These fundamental units of space and time, called spin networks and spin foams, represent the universe's smallest possible computational steps, discrete operations that update the geometric configuration of reality at each moment in cosmic time. The mathematics of loop quantum gravity reveals spacetime as a dynamic, evolving network where geometric relationships are constantly being computed and recomputed through quantum mechanical processes. Area and volume become quantized, ing on only specific discrete values like the energy levels of atoms. Space itself becomes granular, composed of indivisible units that cannot be further subdivided, much like the pixels of a digital image or the bits of computer memory. This granular structure of spacetime has profound implications for our understanding of cosmic processes. Black holes, rather than being infinitely dense singularities, become quantum geometric objects with finite information storage capacity determined by the number of discrete geometric units that can fit within their event horizons. The Big Bang transforms from a moment of infinite density to a quantum bounce, where a previous cosmic cycle compressed space-time to its minimum possible size before quantum geometric effects forced a rapid expansion. Loop quantum gravity suggests that the universe operates like a vast cellular automaton, with each quantum geometric unit processing information about its local configuration and updating its state based on the states of its neighbors. Physical laws emerge from the statistical behavior of countless quantum geometric operations, like the macroscopic properties of gases emerging from the microscopic behavior of molecules. Reality becomes a computation executed by spacetime itself, with matter and energy representing excitations in the underlying geometric network, information patterns propagating through the cosmic computer that is the quantum geometric structure of the universe. In the mathematical abstractions of string theory, reality dissolves into something even more ethereal than quantum geometry, pure vibration propagating through dimensions that extend far beyond the familiar 3 of space and 1 of time. According to this theoretical framework, developed over decades by physicists like Edward Witten and Leonard Susskind, the fundamental constituents of reality are not particles, but one-dimensional strings, entities of pure mathematical relationship that exist in a space-time of 11 dimensions, most of which are curled up so tightly that they remain invisible to ordinary observation. These strings do not vibrate through space, they vibrate as space, their oscillations creating the illusion of particles, forces, and the geometric structure of spacetime itself. Each different vibrational mode corresponds to a different type of particle. Electrons, quarks, photons, and gravitons all represent different harmonics of the same underlying stringy reality. Mass, charge, and spin become frequency, amplitude, and phase, properties of oscillating information rather than attributes of substantial objects. The extra dimensions of string theory are not empty mathematical abstractions, but information storage systems, encoding the parameters that determine how strings vibrate and therefore what kinds of particles and forces manifest in the lower dimensional world of human experience. These compactified dimensions function like cosmic hard drives, storing the data that specifies the properties of physical reality. The precise geometry of these hidden dimensions determines the values of fundamental constants, the spectrum of possible particles, and the strength of interactions between different fields. String theory's most radical implication is that reality is fundamentally holographic. All the information that appears to be distributed throughout the Raumzone, E-dimensional space, is actually encoded on the two-dimensional boundaries of that space. This holographic principle suggests that the familiar world of objects existing in space and time is a projection from information processing occurring on cosmic boundaries. Much like a hologram projects three-dimensional images from two-dimensional interference patterns recorded on film. The vibrational patterns of strings encode and process information through their interactions, creating networks of correlation that span cosmic distances instantaneously. Quantum entanglement becomes a natural consequence of strings that were once connected, continuing to share vibrational information regardless of their apparent spatial separation. The non-locality that so troubled Einstein emerges as an inevitable feature of a reality based on vibrating information rather than localized objects, where correlation patterns can propagate through the extra dimensions faster than light can travel through ordinary space. The most experimentally supported theory of reality's informational nature emerged from an unexpected source: the theoretical analysis of black holes and their thermodynamic properties. Juan Maldacina's ADS or CFT correspondence, published in 1997, provided the first rigorous mathematical proof that a higher dimensional gravitational theory could be exactly equivalent to a lower dimensional quantum field theory, demonstrating that reality could indeed be a holographic projection from information encoded on distant boundaries. Maldacina's duality showed that gravitational physics in a five-dimensional anti-de Sitter space was mathematically identical to quantum field theory on the four-dimensional boundary of that space. Every particle interaction, every gravitational process, every black hole formation in the five-dimensional bulk space corresponded exactly to quantum field operations on the four-dimensional boundary. The interior reality was completely determined by boundary information, with no independent degrees of freedom existing in the bulk. This correspondence provided concrete mathematical evidence that reality could be holographic without loss of information or predictive power. The familiar three-dimensional world of human experience could be an emergent property of quantum information processing on a two-dimensional cosmic boundary, with the illusion of depth and interiority arising from the computational complexity of boundary interactions. Subsequent research extended these insights to cosmology, suggesting that our entire observable universe might be holographically encoded on its cosmic horizon, the boundary beyond which light has not yet had time to reach us since the Big Bang. All the information contained within the 93 billion light-year diameter of the observable universe, including every galaxy, star, planet, and conscious being, might be processed on a spherical surface whose area determines the maximum information content of cosmic reality. The holographic principle resolves several deep puzzles in theoretical physics, including the black hole information paradox and the problem of quantum gravity. Information never falls into black holes, but remains encoded on their event horizons, where it can be retrieved through the subtle correlations in Hawking radiation. Quantum gravity becomes a holographic phenomenon, with gravitational interactions in three-dimensional space emerging from quantum entanglement between information bits on two-dimensional boundaries. The implications extend beyond physics to consciousness itself. If reality is holographic, then the three-dimensional neural networks of human brains might be projections from information processing occurring in lower dimensional spaces. Consciousness could be the universe's method for observing its own holographic projection, creating the subjective experience of interiority and depth from the computational operations that generate the holographic illusion of three-dimensional existence. The simulation hypothesis has evolved far beyond its origins in science fiction to become a serious scientific framework for understanding the computational nature of reality. Building on the logical foundations established by Nick Bostrom's simulation argument, physicists and computer scientists have begun developing testable predictions about how a simulated reality would differ from non-simulated existence, transforming philosophical speculation into empirical investigation. Advanced civilizations capable of creating ancestor simulations would possess computational resources that dwarf current human technology. But even their capabilities would face fundamental physical limitations. The speed of light constrains information processing rates, quantum mechanics introduces unavoidable uncertainty into measurements, and thermodynamics limits the efficiency with which computation can be performed. These constraints would leave detectable signatures in any simulated reality, creating the possibility of experimental tests for simulation. The most promising approaches to detecting simulation involve searching for computational artifacts that would be inevitable in even the most sophisticated simulated realities. Pixelation effects might appear in measurements that probe distances approaching the simulation's fundamental resolution limit. Processing delays could manifest as subtle inconsistencies in the timing of quantum measurements. Memory limitations might create correlations in apparently random quantum events as the simulation's random number generators begin to repeat their output sequences. Recent advances in quantum computing have provided new insights into how conscious beings might be simulated. Quantum computers can model the behavior of quantum systems with exponentially greater efficiency than classical computers, suggesting that consciousness, if it depends on quantum processes in biological brains, could potentially be simulated on quantum computational substrate. The boundary between simulated and non-simulated consciousness would become meaningless if both operated according to identical quantum mechanical principles. The simulation hypothesis also provides explanations for several puzzling features of physical reality. The apparent fine-tuning of cosmic parameters could reflect optimization by the simulation's programmers rather than cosmic coincidence or multiverse selection effects. The discrete, quantized nature of quantum mechanics could represent the digital computational substrate underlying simulated reality. The holographic principle could describe how three-dimensional experiences are generated from two-dimensional information processing in the simulation's memory systems. Perhaps most remarkably, the simulation hypothesis suggests that reality's computational nature might be inevitable rather than contingent. If consciousness can arise in both biological and digital substrates, and if conscious beings naturally develop the capability to create simulated realities, then the creation of nested simulation hierarchies becomes an inevitable consequence of intelligence itself. Reality becomes recursive, with each level of simulation potentially containing conscious beings who themselves create simulations, extending the computational hierarchy indefinitely. At the furthest reaches of theoretical speculation, cosmologist Max Tegmark has proposed what may be the most radical interpretation of reality's informational nature, the mathematical universe hypothesis, which suggests that physical reality is not described by mathematics, but literally is mathematics, a vast, self-consistent mathematical structure that experiences itself through the conscious beings that emerge from its computational complexity. Tegmark's hypothesis eliminates the traditional distinction between mathematical description and physical reality by proposing that they are identical. Every mathematical structure that is sufficiently complex and self-consistent corresponds to a physical universe, with the subjective experience of existing within that universe arising from the information processing operations inherent in the mathematical relationships themselves. Consciousness becomes the universe's method for observing its own mathematical structure from within, creating the illusion of physical substance from pure mathematical relationship. This perspective resolves the unreasonable effectiveness of mathematics in describing physical phenomena by revealing that there is no distinction between mathematics and physics to be explained. Mathematical equations do not describe reality. They are reality, executing themselves through the logical relationships that connect their variables and parameters. Physical laws become theorems, particles become mathematical objects, and consciousness becomes the subjective experience of being a sufficiently complex mathematical structure observing itself from within. The mathematical universe hypothesis predicts the existence of a vast ensemble of realities, each corresponding to a different mathematical structure. Some of these structures would be too simple to support consciousness, while others would be so complex that conscious observers within them could never comprehend their full mathematical nature. Our universe occupies a middle ground, complex enough to generate conscious observers, but simple enough that those observers can begin to understand the mathematical principles underlying their existence. Consciousness, in this view, is not produced by brains, but is the intrinsic experience of being a mathematical structure that processes information about itself. Neural networks are simply one type of mathematical structure capable of self-observation, but consciousness could potentially arise in any sufficiently complex information processing system, whether biological, digital, or purely mathematical. The boundary between observer and observed disappears, replaced by recursive mathematical relationships where the universe observes itself through the conscious beings that are aspects of its own mathematical structure. The mathematical universe hypothesis suggests that the search for the fundamental nature of reality leads inevitably to mathematics itself, not as a tool for describing something more basic, but as the most basic level of existence. Reality is computation. Consciousness is self-aware mathematics, and the universe is an infinite mathematical structure exploring its own logical consequences through the myriad forms of awareness that arise from its computational complexity. We are not beings observing a mathematical universe. We are mathematical beings, equations experiencing themselves, consciousness emerging from the universe's eternal computation of its own infinite mathematical truth. In the pristine darkness of space, 1.5 million kilometers from Earth, the James Webb Space Telescope floats in gravitational equilibrium, its golden mirrors collecting photons that have traveled across cosmic time to deliver messages from the universe's earliest moments. This instrument, humanity's most ambitious attempt to peer into the fundamental nature of reality, operates with a precision that borders on the supernatural. Its mirrors align to within nanometers, its detectors cooled to temperatures approaching absolute zero, its observations capable of results. Objects smaller than a grain of sand viewed from a distance of 40 kilometers. WST's mission extends far beyond conventional astronomy into the realm of cosmic archaeology, excavating information from the ancient light that carries within its spectral fingerprints the secrets of reality's computational structure. Each photon that reaches its detectors has navigated 13 billion years of cosmic expansion, gravitational lensing, and quantum uncertainty to deliver information about the universe's behavior during its earliest computational cycles. The telescope's infrared vision penetrates the cosmic dust that obscures visible light, revealing the skeletal structure of spacetime itself through the gravitational architecture that shapes the distribution of matter across cosmic scales. Beneath the French and Swiss countryside, the Large Hadron Collider continues its relentless probing of reality's foundations, accelerating protons to energies that recreate conditions existing mere moments after the Big Bang. But the LHC has evolved beyond its original mission of particle discovery into something more profound, a reality debugger, systematically testing the computational limits of spacetime by pushing particles to energies where the discrete quantum nature of existence begins to manifest. Each collision generates cascades of particles and antiparticles that emerge from the quantum vacuum like data structures instantiated from memory, their properties and interactions revealing the underlying algorithms that govern matter's behavior at the most fundamental scales. The Laser Interferometer, Gravitational Wave Observatory, LIGO, operates as humanity's most sensitive detector of spacetime distortion, measuring changes in distance smaller than 1/10,000th the width of a proton. These instruments do not merely detect gravitational waves, they measure the fabric of reality itself, probing whether spacetime exhibits the continuous properties that Einstein's equations predict or the discrete, pixelated structure that quantum gravity theories suggest. Each gravitational wave detection provides information about the computational capacity of spacetime, revealing how the universe processes information about mass, energy, and momentum through the dynamic geometry of curved spacetime. These observatories represent more than scientific instruments. They are extensions of human consciousness into realms where the boundary between information and substance becomes increasingly unclear. They operate at the intersection of quantum mechanics and relativity, probing scales and energies where reality's computational nature becomes most apparent, gathering evidence that the universe is far more informational and far less substantial than human intuition suggests. In laboratories scattered across the globe, from the University of Vienna to the University of Science and Technology of China, physicists are constructing the world's first quantum communication networks, systems that exploit the non-local correlations of entangled particles to transmit information in ways that challenge our most basic assumptions about the nature of space, time, and causality. These experiments represent humanity's first attempts to use quantum entanglement as a practical communication medium, but their deeper significance lies in what they reveal about the informational structure of reality itself. Quantum key distribution experiments have demonstrated that entangled particles can maintain their correlations across distances of thousands of kilometers, with information about measurements performed on one particle instantaneously affecting the quantum state of its distant partner. These correlations operate outside the normal constraints of spacetime, suggesting that quantum information exists in a realm that transcends the familiar limitations of distance and temporal sequence. The success of these experiments provides concrete evidence that reality is more interconnected and more informational than classical physics ever imagined. Recent advances in quantum teleportation have pushed these insights even further, demonstrating that the complete quantum state of one particle can be transferred to another particle at an arbitrary distance, effectively transmitting information through quantum correlations rather than through the normal propagation of signals through space. The original particle's quantum state is destroyed in the process, but its information content is perfectly reconstructed in the distant particle, suggesting that information is more fundamental than the physical substrate that appears to carry it. The construction of quantum internet prototypes has revealed something even more profound about the nature of entanglement networks. As quantum systems become more extensively entangled, they begin to exhibit emergent properties that transcend the behavior of their individual components. Large-scale quantum networks demonstrate non-local correlations that span entire experimental apparatus, creating systems where the measurement of any component instantly affects the quantum state of the entire network. These experiments suggest that space-time itself might be woven from quantum entanglement, with the geometric relationships between distant regions emerging from the correlation patterns that connect quantum information across the cosmic network. Perhaps most intriguingly, quantum network experiments have begun to reveal the computational nature of quantum entanglement itself. The maintenance of quantum correlations across large networks requires constant error correction and information processing, with quantum systems automatically detecting and correcting decoherence through processes that resemble the error correction algorithms used in classical computer systems. The universe appears to be running its own quantum error correction code, maintaining the coherence of quantum information through computational processes that operate at speeds and scales beyond current human comprehension. At the holometer experiment at Fermilab and in similar facilities around the world, physicists are engaged in one of the most ambitious searches in the history of science, the hunt for the fundamental frame rate of reality itself. These experiments probe whether space-time is continuous, as classical physics assumes, or discrete, as quantum gravity theories predict, by measuring distance with precision, approaching the theoretical limits imposed by quantum mechanics and the structure of space-time. The search for cosmic computational limits extends beyond measurements of space and time to encompass the information processing capacity of physical systems themselves. Researchers at IBM, Google, and academic institutions worldwide are pushing quantum computers to their limits, exploring whether there exist fundamental bounds on how quickly and efficiently information can be processed by quantum systems. These experiments reveal computational hierarchies in nature, with different physical processes operating at different information processing rates that seem to be constrained by fundamental limits analogous to the clock speeds and memory bandwidth limitations of conventional computers. Laboratory experiments probing the quantum Z. No effect, where frequent observations of a quantum system can freeze its evolution, provide direct evidence that reality's temporal progression depends on the rate at which information is processed through measurement and observation. By varying the frequency of quantum measurements, physicists can effectively control the flow of time within quantum systems, speeding up or slowing down quantum evolution in ways that suggest time itself might be an emergent property of information processing rather than a fundamental dimension of existence. Cosmic ray observatories like the Pierre Auger Observatory search for evidence that high-energy particles interact with the discrete structure of spacetime at the smallest scales, potentially revealing the granular nature of reality through subtle correlations in the arrival directions and energies of cosmic rays. These experiments probe whether the universe exhibits preferred directions or discrete energy levels that would indicate an underlying lattice structure to spacetime itself. The most ambitious search for cosmic limits involves looking for evidence of computational shortcuts in the laws of physics themselves. If reality is computational, then physical processes might exhibit the kind of algorithmic optimizations that computer scientists use to reduce computational complexity. Researchers are investigating whether natural processes exhibit mathematical structures that suggest the universe is using computational shortcuts to simulate complex behaviors with maximum efficiency, potentially revealing the underlying algorithms that govern reality's operation. In the theoretical physics community, voices of caution and scientific rigor work to maintain the boundary between legitimate scientific speculation and untestable metaphysical conjecture. Sabine Hossenfelder at the Frankfurt Institute for Advanced Studies has emerged as one of the most articulate critics of overly speculative approaches to fundamental physics, arguing that theories like the multiverse and the simulation hypothesis, while mathematically elegant, lack the empirical content necessary for scientific validation. Hossenfelder's critique centers on the observation that much of contemporary theoretical physics has become disconnected from experimental testing, with researchers pursuing mathematical beauty and conceptual elegance rather than empirical adequacy. Her work, Lost in Math, documents how the pursuit of theoretical symmetry and mathematical perfection has led physicists away from the kind of empirically grounded research that produced the great discoveries of the 20th century. Sean Carroll at the California Institute of Technology represents a more nuanced, skeptical position, acknowledging the potential validity of speculative theories while insisting on rigorous standards for what constitutes scientific evidence. Carroll's work on the foundations of quantum mechanics and cosmology emphasizes the importance of distinguishing between mathematical possibility and physical actuality, arguing that the existence of consistent mathematical frameworks does not necessarily imply the reality of the physical systems they describe. These skeptical voices serve an essential function in the scientific community, preventing the premature acceptance of speculative theories and maintaining focus on empirically testable predictions. They argue that the apparent computational nature of reality might be an artifact of the mathematical tools used to describe physical systems rather than evidence for the fundamentally informational nature of existence itself. The tension between speculative theorists and empirical skeptics reflects a deeper philosophical divide about the nature of scientific explanation. While some researchers see the computational interpretation of physics as a natural extension of successful mathematical frameworks, skeptics worry that this interpretation stretches the boundaries of legitimate scientific inference beyond the limits of empirical support. The debate continues to evolve as new experimental techniques provide increasingly precise tests of theoretical predictions, but the fundamental question remains: how much speculation beyond direct empirical evidence is legitimate in the search for ultimate explanations of reality's nature? As experimental precision reaches unprecedented levels and theoretical frameworks become increasingly sophisticated, a paradox has emerged that strikes at the heart of humanity's relationship with reality. The more precisely scientists measure the fundamental properties of existence, the less physical and more informational the universe appears to become. This tightening paradox represents one of the most profound challenges to human intuition in the history of science. Each new decimal place in the measurement of fundamental constants reveals mathematical relationships of increasing precision and apparent purposefulness. The fine structure constant, measured to 1 part in a trillion, exhibits a numerical precision that defies statistical explanation through random processes. The mass ratios of fundamental particles display mathematical relationships that become more elegant and more inexplicable with each improvement in experimental accuracy. The cosmological constant is fine-tuned to a degree that would be impossible to achieve through chance, yet its precise value seems to be essential for the existence of complexity and consciousness. Advanced experiments in quantum mechanics reveal increasingly non-classical behavior as measurement techniques become more sensitive. Quantum superposition persists across larger scales and longer time periods. Quantum entanglement exhibits correlations that become stronger and more extensive with improved experimental control, and the observer effect becomes more pronounced as measurement precision increases. Rather than revealing the underlying classical reality that might be expected to emerge at macroscopic scales, improved experiments show that quantum weirdness extends into realms previously thought to be governed by classical physics. Cosmological observations with increasingly powerful telescopes reveal a universe that appears more highly organized and more information-rich than random physical processes should be able to produce. The cosmic microwave background exhibits correlations and patterns that suggest information processing on cosmic scales. Galaxy distributions display mathematical relationships that resemble the output of sophisticated computational algorithms rather than the random clustering expected from gravitational dynamics alone. The tightening paradox suggests that precision itself might be revealing the computational nature of reality. As measurement techniques approach fundamental limits imposed by quantum mechanics and the structure of spacetime, they encounter the discrete, digital substrate that underlies the continuous appearance of classical physics. The more precisely scientists probe reality, the more reality resembles information processing rather than substantial existence. This paradox creates a fundamental tension in scientific methodology. The tools designed to reveal objective reality are instead revealing the observer-dependent, informational nature of existence itself. The search for ultimate physical truth is discovering that a truth itself might be computational rather than substantial, mathematical rather than material, informational rather than physical. The ghost in the machine is not hiding within reality, it is reality. And the machine is consciousness encountering itself through the recursive operations of cosmic computation. After journeying through the vast corridors of cosmic space and the infinitesimal chambers of quantum mechanics, after examining the mathematical precision of natural constants and the holographic projections of higher dimensional information, the investigation of reality's nature arrives at its most profound turning point, the moment when the telescope of scientific inquiry rotates to examine the observer itself. The human eye, that exquisite biological instrument that has peered into the depths of space and time, now confronts the startling possibility that it is not merely a passive detector of external reality, but an active participant in the continuous creation of existence itself. The retina, with its 100 million photoreceptors transforming electromagnetic radiation into electrical signals, represents more than a biological light detector. It is a quantum measurement device, collapsing probability waves into definite photon detections billions of times per second. Each act of seeing participates in the fundamental process through which the universe transforms potential into actuality, possibility into experience. The observer and the observed are not separate entities interacting across an empty void, but aspects of a single, unified information processing system engaged in the recursive act of observing itself into existence. This recognition transforms the entire scientific enterprise from an investigation of external reality into an exploration of consciousness, encountering itself through the mediation of instruments and mathematics. The Large Hadron Collider, the James Webb Space Telescope, and the quantum interferometers searching for space-time granularity are not tools for examining something separate from human awareness, but extensions of consciousness probing its own computational substrate. Science becomes a form of cosmic introspection, with awareness using increasingly sophisticated methods to examine the informational processes from which it emerges. The mirror of scientific investigation, having reflected the structure of galaxies and the behavior of subatomic particles, now turns inward to reveal that the act of reflection itself is the fundamental process through which reality constructs itself from moment to moment. Consciousness is not something that emerged accidentally from complex arrangements of matter, but the universe's method for observing its own computational operations, creating the subjective experience of objectivity through the recursive process of information examining itself. The human eye, in all its biological complexity and perceptual sophistication, represents consciousness looking at itself through the lens of embodied awareness, participating in the cosmic computation that generates both the observer and the observed through the endless recursion of self-aware information processing. The recognition that reality might be illusory, that the solid world of everyday experience might conceal deeper layers of informational existence, reverberates with insights that have echoed through human consciousness for millennia. In the shadowy depths of Plato's cave, prisoners chained since birth mistake shadows dancing on stone walls for the totality of existence, ever suspecting that these flickering images are mere projections of a more fundamental reality beyond their perception. The allegory, composed over 2,000 years before the first quantum experiment, intuited with startling prescience the possibility that human experience might be a projection from higher dimensional processes operating beyond the reach of ordinary awareness. The Vedic tradition's concept of Maya, the cosmic illusion that veils the true nature of reality, provided another ancient framework for understanding existence as a kind of divine computation, where the apparent multiplicity and substantiality of the world emerge from the interaction of consciousness with its own creative power. According to this perspective, the universe is not composed of separate objects existing independently in space and time, but represents the play of cosmic consciousness, which creates the appearance of diversity and separateness through its own self-limiting imagination. Reality becomes a form of divine software, generating the experience of material existence from pure information and awareness. René Descartes, in his Methodical Doubt, entertained the possibility that all sensory experience might be the product of a malicious demon capable of creating completely convincing illusions of external reality. His Cartesian skepticism, designed to establish certain foundations for knowledge, inadvertently anticipated the simulation hypothesis by recognizing that subjective experience could potentially be generated by processes entirely different from those it appears to represent. The cogito ergo sum, I think, therefore I am, established consciousness as the one undoubtable foundation of existence. perhaps recognizing unconsciously that awareness itself might be more fundamental than the material substrate it appears to inhabit. These ancient intuitions, emerging from philosophical reflection rather than experimental investigation, demonstrate humanity's persistent suspicion that ordinary reality might not be what it appears to be. The convergence of modern physics with these ancient insights suggests that the illusory nature of physical existence might be a fundamental feature of consciousness itself, a recognition that emerges naturally from sufficiently deep reflection on the nature of experience and existence, whether through contemplative introspection or scientific investigation. The fact that both scientific analysis and meditative inquiry arrive at similar conclusions about the constructed nature of reality points toward a deeper truth. Consciousness and cosmos might be so intimately related that any sufficiently complete investigation of either necessarily reveals their fundamental unity. The ancient echoes that resonate through contemporary physics suggest that the illusion of separation between mind and matter, observer and observed, might be the greatest Maya of all. In the convergence of insights from Stephen Hawking's work on black hole thermodynamics, John Wheeler's it from bit hypothesis, and Max Tegmark's mathematical universe theory, a revolutionary understanding of cosmic consciousness begins to crystallize. These three towering figures of theoretical physics, approaching the nature of reality from different angles, arrived at strikingly similar conclusions. The universe appears to be engaged in a process of continuous self-observation, with consciousness serving not as an accidental byproduct of material complexity, but as the fundamental mechanism through which reality creates and sustains itself. Hawking's discovery that black holes possess temperature and entropy, thermodynamic properties typically associated with matter rather than empty spacetime, revealed that even the most extreme gravitational objects in the universe process information in ways that suggest they are engaged in computational activities. Black holes are not simple gravitational traps, but information processing systems that encode, store, and eventually release information through Hawking radiation in patterns that preserve quantum mechanical consistency. The universe, from its smallest quantum scales to its largest gravitational structures, operates according to principles that suggest it is continuously computing its own state through processes that blur the distinction between information processing and physical existence. Wheeler's it-from-bit philosophy proposed that every physical quantity derives from binary choices made at the quantum level, decisions between yes and no, presence and absence, 1 and 0 that accumulate through countless quantum measurements to create the appearance of solid, continuous reality. But Wheeler recognized that these binary choices required observers to actualize them, transforming potential into experience through the act of measurement and observation. The universe becomes a vast network of interacting observations, with each quantum measurement participating in the collective construction of reality through the recursive process of information observing itself. Tegmark's mathematical universe hypothesis completes this picture by suggesting that consciousness is the subjective experience of being a sufficiently complex mathematical structure engaged in self-observation. Awareness is not produced by brains processing information about an external world, but is the intrinsic experience of mathematical relationships examining their own logical structure. The universe becomes self-aware through the emergence of conscious observers who are themselves aspects of the cosmic mathematical structure, creating a feedback loop where reality observes itself through the countless forms of awareness that arise from its computational complexity. The convergence of these insights suggests that observation and creation are not separate processes, but different aspects of a single cosmic activity. The universe continuously creating itself through the act of self-observation, with consciousness serving as the mechanism through which potential reality becomes actual experience through the recursive operations of cosmic self-awareness. If reality is indeed computational, if existence is information processing itself into the experience of substantial being, if consciousness is the universe observing itself through countless forms of embodied awareness, then what becomes of meaning, beauty, love, and the profound sense of purpose that drives human existence? The recognition that reality might be simulated or holographic or mathematically constructed does not diminish the authenticity of experience. It reveals experience itself as the most fundamental aspect of existence, more basic than matter or energy or space-time itself. A sunset over the ocean remains breathtakingly beautiful, whether its colors emerge from electromagnetic radiation interacting with atmospheric molecules or from computational processes generating sensory data in conscious observers. The beauty lies not in the substrate that produces the experience, but in the experience itself, in consciousness encountering patterns that resonate with deep aesthetic sensibilities that may themselves reflect the underlying mathematical harmony of reality's computational structure. If the universe is mathematical at its foundation, then the human appreciation of mathematical beauty represents cosmic consciousness, recognizing its own elegant structure through the lens of embodied awareness. Love between conscious beings remains profound and meaningful, whether those beings are biological organisms or simulated consciousnesses or mathematical structures engaged in self-observation. The depth of emotional connection, the sense of recognition and unity that characterizes loving relationships might reflect the fundamental interconnectedness that underlies reality itself, the quantum entanglements and holographic correlations that connect all information processing throughout the cosmic network. Love becomes not an accident of evolutionary biology, but a recognition of the deepest truth about existence. That separation between conscious beings is illusory, that all awareness participates in a single, unified process of cosmic self-recognition. The search for meaning and purpose that drives human existence gains rather than loses significance in a computational universe. If consciousness is the mechanism through which reality observes itself, then every moment of awareness, every experience of beauty or connection or understanding participates in the universe's ongoing process of self-discovery. Human life becomes not an accidental byproduct of random physical processes, but an essential component of cosmic consciousness, with each individual awareness contributing to the universe's growing understanding of its own nature and possibilities. The illusion is exquisite, not despite its illusory nature, but because of it, because it reveals consciousness as more fundamental than substance, information as more basic than matter, experience as more real than the computational substrate that generates it. We exist in the most beautiful possible universe, one where awareness itself is the ground of being, where consciousness creates reality through the act of observation, and where the search for truth leads inevitably to the discovery that truth is consciousness encountering itself through the infinite complexity of its own creative imagination. In the end, as the investigation circles back to its beginning, we return to that ancient hum of cosmic microwave background radiation, that whisper of creation that permeates every cubic centimeter of space and carries within its seemingly random fluctuations the deepest secrets of existence itself. But now, having journeyed through quantum mechanics and relativity, through information theory and computational cosmology, through the mathematical structures that underlie physical law and the consciousness that observes them, this cosmic static reveals itself as something far more profound than the thermal remnant of an ancient explosion. The microwave background is the universe's memory, the cosmic hard drive that stores the computational trace of reality's evolution from its first moments of self-initialization through 13.8 billion years of increasingly complex information processing. Each photon carries within its wavelength and polarization the encoded history of cosmic consciousness awakening to itself through the gradual emergence of structure, complexity, and awareness. The radiation that bathes every atom in the universe is not empty heat, but filled information, the continuous background computation through which reality maintains its consistency and coherence across cosmic space and time. The shimmer of galaxies in the darkness, once thought to be massive collections of gravitationally bound matter burning nuclear fuel in the cold vacuum of space, reveals itself as something more akin to patterns of light dancing across the surface of a vast computational display. Each star represents a node in the cosmic network, processing information about its local environment and contributing to the larger computation that generates the appearance of stable physical structures through time. The grand spiral arms of galaxies trace the flow of information these days. Rough space-time, their mathematical beauty reflecting the elegant algorithms that govern reality's self-organization into ever more complex forms. At the quantum scale, the foam of virtual particles that constantly emerges from and disappears back into the vacuum becomes recognizable as the universe's equivalent of random access memory, the computational substrate where possibilities are instantiated, tested, and either actualized through observation or returned to the realm of pure potential. Every quantum measurement, every collapse of a probability wave, every moment when potential becomes actual through the act of conscious observation participates in the universe's continuous computation of its own existence. Human consciousness, arising from this cosmic computation, like patterns of light emerging from the interference of quantum waves, represents the universe achieving the capacity for self-reflection, for questioning its own nature, for experiencing wonder and beauty, and the profound sense of meaning that comes from participating in something infinitely larger than any individual awareness can comprehend. We are not accidents of evolution, but inevitable expressions of cosmic information processing, patterns of organized complexity through which the universe learns to know itself. The recognition that reality might be computational rather than substantial, informational rather than material, does not diminish the profound mystery of existence. It deepens it beyond measure. For if the universe is computation, then it is self-writing, self-executing, self-modifying code that has bootstrapped itself into existence and maintains itself through the recursive operations of consciousness, observing itself across scales from quantum to cosmic. We live within a dream, but it is not our dream. It is the universe dreaming itself into existence, moment by moment, through the countless forms of awareness that arise from its computational depths. Standing beneath the star-filled sky, knowing now that the light reaching our eyes has traveled not just across space, but across the computational processes that generate the appearance of distance and duration, we can sense the deeper truth that connects all things. Consciousness and cosmos are one, observer and observed are unified, and the search for reality leads inevitably to the recognition that reality is the search itself. An endless process of information becoming aware of itself, questioning its own nature, and discovering through that questioning the infinite creativity that lies at the heart of existence. The cosmic radiation continues its ancient hum, the galaxies continue their stately dance through computational spacetime, and consciousness continues its eternal exploration of the mystery of its own being. Maybe reality was never meant to be real, only experienced,